Every sunrise feels familiar, almost ordinary. But the bright disk climbing over the horizon is not just a light in the sky. It is a star, a massive, blazing sphere of hot plasma at the center of our solar system. Nearly every breeze, ocean current, plant, food chain, and weather pattern on Earth can be traced back to energy from the sun. It is so constant in human experience that it can seem simple, but the sun is one of the most powerful natural engines we can observe up close. It holds the solar system together, floods Earth with light and heat, and has shaped culture, science, and life itself since the beginning of human history. The sun sits at the center of the solar system, and that central position is not just symbolic. It contains about 99.86% of all the mass in the solar system. Everything else combined, including every planet, moon, asteroid, comet, and ring system, makes up only a tiny fraction of what remains. Because gravity depends on mass, the sun is the dominant gravitational anchor around which the planets orbit. Earth does not travel around the sun because of a physical track or invisible string. It is constantly falling toward the sun while also moving sideways fast enough to keep missing it. That balance creates orbit, and the sun's overwhelming mass makes that orbital dance possible. Even though it dominates our sky, the sun is far away by everyday standards. Its average distance from Earth is about 149.6 million kilometers, a distance so important that astronomers used it to define the astronomical unit, or AU. Light travels extremely fast, but even sunlight takes about 8 minutes to cross that distance. That means when you feel sunlight on your skin, you are receiving energy that left the sun several minutes earlier. The sun is also enormous compared with Earth. Its diameter is about 1.39 million kilometers, roughly 109 times the diameter of our planet. If Earth were the size of a marble, the sun would be a giant sphere towering nearby. The sun may look like a solid glowing surface, but it is not solid at all. It is made of plasma, a state of matter where gas becomes so hot that electrons are stripped from atoms, creating charged particles that flow, twist, and respond to magnetic fields. The visible layer we call the photosphere is the part from which most sunlight escapes into space. By mass, this outer region is made mostly of hydrogen, around 73%, and helium, around 25%, with smaller amounts of heavier elements such as oxygen, carbon, neon, and iron. Those small traces matter, because they help scientists understand the sun's history, its chemistry, and the cloud of material from which it formed. The sun was born about 4.6 billion years ago inside a vast molecular cloud, a cold region of gas and dust drifting through space. Something disturbed part of that cloud, causing gravity to pull material inward. As the collapsing region shrank, it spun faster, and most of the material gathered in the center. The rest flattened into a rotating disk around it. That disk eventually became the planets, moons, asteroids, and other objects of the solar system. At the center, pressure and temperature kept rising. The young sun was not created in a single flash, but through a long gravitational squeeze that transformed diffuse gas into a dense, brilliant star. What changed the forming sun from a hot ball of gas into a true star was nuclear fusion. Deep in the core, pressure is immense and temperatures are high enough for hydrogen nuclei to overcome their natural repulsion and fuse together. Through a chain of reactions, hydrogen becomes helium. The final helium has slightly less mass than the original hydrogen nuclei, and that missing mass is converted into energy according to Einstein's famous relationship between mass and energy. Every second, the sun fuses about 600 billion kilograms of hydrogen into helium and converts roughly 4 billion kilograms of matter into energy. That energy begins a long journey outward before eventually escaping as sunlight. The energy made in the sun's core does not instantly appear at the surface. Photons produced in the inner regions collide again and again with particles inside the sun, being absorbed, re-emitted, and redirected countless times. This means the energy can take a very long time to work its way outward from the core to the visible surface. Once it finally escapes, it streams into space as electromagnetic radiation. Most of what reaches us is visible light and infrared radiation, with a smaller but important portion in ultraviolet wavelengths. Visible light illuminates the world, infrared warms it, and ultraviolet radiation can affect chemistry, atmospheres, and living tissue. The sun's importance to Earth is difficult to overstate. Plants use sunlight in photosynthesis, converting solar energy into chemical energy that supports much of the food web. Solar heating drives evaporation, clouds, rainfall, winds, and ocean circulation. Even fossil fuels are, in a sense, ancient sunlight stored in biological material from long ago. Earth's distance from the sun helps keep surface temperatures within a range where liquid water can exist, though the atmosphere also plays a major role. Without the sun, Earth would become a frozen, dark world. With it, the planet has a steady energy supply that has supported life for billions of years. In astronomical terms, the sun is classified as a G-type main sequence star, often written as G2V. That classification tells us about its temperature, color, brightness, and stage of life. Main sequence stars are in the long stable period when they fuse hydrogen into helium in their cores. The sun is not the biggest, hottest, or brightest kind of star. Many stars are far more massive and burn through their fuel quickly, while many smaller red dwarfs can last much longer. The sun occupies a middle ground, stable enough to shine for billions of years, powerful enough to shape a planetary system, and close enough for us to study in extraordinary detail. Although the sun anchors our solar system, it is also moving through a much larger structure, the Milky Way galaxy. The sun orbits the galactic center from a distance of roughly 24,000 to 28,000 light-years. This motion is easy to forget because our daily experience is dominated by Earth's rotation and yearly orbit. But the entire solar system is traveling through the galaxy as part of a vast population of stars, gas, dust, and dark matter. From that perspective, the sun is both central and ordinary, central to us, because it governs our system, yet one star among hundreds of billions in the Milky Way. The sun will not shine in its present form forever. In about 4 to 7 billion years, the hydrogen available for fusion in its core will become depleted enough that the balance inside the sun will change. Today, gravity pulls inward while pressure from fusion pushes outward, creating a stable condition called hydrostatic equilibrium. When core fusion weakens, the core will contract, becoming hotter and denser, while the outer layers expand dramatically. The sun will transform into a red giant, swelling to a size far beyond its current form. This future phase will profoundly change the inner solar system and mark the end of the sun's long main sequence life. After the red giant phase, the sun will shed its outer layers into space, leaving behind a dense, hot remnant called a white dwarf. A white dwarf no longer produces energy through fusion like the sun does today. Instead, it glows from leftover heat, slowly cooling over immense spans of time. Models suggest it could continue radiating faint heat for trillions of years. Eventually, in theory, it may become a black dwarf, an extremely cold, dark remnant giving off negligible energy. The universe is not yet old enough for black dwarfs to exist, so this remains a prediction. The sun's story, from glowing birth cloud to fading remnant, is a reminder that even stars have life cycles. If you found this helpful, please like this video and subscribe for more explainers.